Hi, good evening, everyone, and thanks all for joining us today for our Mydbops My Webinar 48 on scaling to 920 million users, our TiDB story. I'm Shiny from Mydbops, and I'll be hosting today's webinar. For today's webinar, we have Kabilesh PR as a speaker. He's a founding partner at Mydbops. He has been working with databases for more than 13 years. And he's the first certified TiDB professional in India. He's also a TiDB champion recognized by the TiDB community. So you're going to hear the story from someone who works with databases every day. So in this webinar, Kabilesh will walk us through a real migration story that is for a streaming platform with 920 million users, the problems they faced with MySQL and how they solved it with TiDB, and what they learned along the way during the migration. And this session is being recorded, and you will receive the recording and the slides after this webinar. So please keep your questions ready and post them in the Q&A or chat at the end of the session. We will get the answers during the Q&A. So Kabilesh, can you start sharing your screen?
Sure, Sani. 1 second. Please let me know if you can see my screen.
Yes, it's perfect.
Okay.
I hope everyone can see.
See the screen, right?
Yes. You can start, Kabilesh. Thank you.
Okay. Hi, good afternoon, everyone. So myself, Kabilesh PR. Thanks for being a guest, and we'll be presenting this webinar. Welcome to the 40th webinar, scaling to 920 million users. Okay, so I'll try to cover this as a story. So what we did with respect to the customer, what was the scaling point, what was the issue, problems, bottlenecks, and the workaround which I have done during the migration. Okay, so Shiny gave a good introduction about me. If you want to know more about me, I'm very active in LinkedIn. You can scan this QR code and be connected on the LinkedIn. Okay. So who we are, MyDBOps, we are a trusted open source database partners for enterprise clients, and wherever your database is hosted, we support them. So we have around 9+ years of expertise, and by numbers, we are into 10th year, close to 10th year. We have around 800+ happy clients, and we handle petabytes of transaction across all our clients, 6,000+ managed services, server, and multiple soft tickets. So these are the database technologies that we work predominantly. That is MySQL. We started with MySQL, then we entered into Mongo, Postgres, MariaDB, and TiDB. So I head the TiDB division, and I'm actively working on this along with my team members. Okay, so these are the two modes of engagement on which MyDBOps works. That is a targeted engagement, that is consulting services, wherein we provide project-based support, and managed services is your 24/7 DB on these technologies: MySQL, MariaDB, Mongo, Postgres, and TiDB. Okay, so with this, I'll just straight away jump onto the topic. I'll try to keep it to cover the story. I'll just give a brief introduction about the customer. So this customer is a SaaS-based cloud software billing customer for OTT platforms. So you might be using OTT in day-to-day life, right? Like Hotstar, Sony, etc., multiple things. So this customer has his clients are like the OTT platform. They maintain the subscription of the users. Let's say Geo Hotstar, they might be having n number of users. This user management is done by this client. So what is the main thing is they manage the login, that is OTPs, the premium accounts. So what kind of account, it's a premium, basic, or those things, and also the subscription model, like what kind of subscription they have, the ages, and multiple other things, and they collect and manage the user for their clients. Okay, so they are serving this service in around 180 countries, and they have around 920 million users. So global user is 920 million users. Okay, so I'll touch upon the current DB architecture. So they are present in managed MySQL services by the public cloud offering. So they have one writer and two readers. The writer is around 48 CPUs and 384 GB RAM, and the reader is 48 core, and this is the reader configuration. Okay, so this is their BU configuration. BU in the sense on a normal working day and the normal business hour, this is their idle configuration. Uh, and the dataset size is around 7 terabyte, and they are multi-AZ deployments. So next comes the scaling requirements. The important part starts from here. Like on as a OTT platform, you know, right? So when there is a huge event like an IPL or some major snowball or some event is going on, so people comes in flood. Okay, so this was one kind of a requirement wherein client was for the upcoming rivalry event. That means they do not, these two countries play very rarely, okay, on their platform. So they were anticipated with a traffic of around 3 million QPS, okay, which is, and also importantly, the latency part is very important because they said that they need to have a P99 latency, which is less than 20 ms. That is DB latency should be less than 20 ms, because after post the 20 ms, what happens is they have multiple components of the application. So it starts queuing and their application goes down eventually. So this is the critical problem statement which they have given. So this 3 million QPS on the database is getting translated to 25K application TPS. Okay, so this is based upon the load test we have done. Okay, this is a requirement for this journey of migration and scaling. Okay, the initial scaling. So as we discussed, right, the BAU server setup wherein they have one master and two readers. Initially, the initial scale was done on this particular existing setup. So so migration is a very difficult thing, right? They have to make code changes and multiple things are involved. So first they scaled the current architecture, that means current in-house server. Like the master was scaled to 48x large, and they added two more read replicas to handle more read scalability. Okay, and they started the load testing. Okay, these instances, that is 48x large, this is the highest capacity of instance, post which this cloud provider does not provide an instance type. Okay, so this is the highest instance. So they started the load test. With the load test, they were able to handle only 10K TPS. So the 10K TPS translates to 300K QPS, that is 3 lakh QPS in the database. And the test failed. The post which they started seeing high latencies, high commit throughputs, high write latency, and their application eventually, as we discussed, right, it failed. Okay, this is the first test. And later they took this problem statement to the cloud vendor. Okay, so the cloud vendor sat together, they appointed their engineers, they ran to their office, they started working on the problem statement. So they said, yes, we can scale, and they started applying the patches, variable changes to the current existing system. Okay, and they ran multiple series of tests, and post which they came with the solution that adding Redis on top of this MySQL component can reduce the read pressure. And also Cassandra, that is key spaces, they will move to write heavy log tables, that is the device information tables and the XML payload tables, which they are storing in a log based table, will be moved to the Cassandra so that the write pressure reduces on the servers. Okay, so this was the updated architecture in the second phase. So they again started the load test with the from the failure. That means 10K, from 10K they started testing 11, 12. So during the 12, this setup was able to handle only up to 12K of TPS, that is 365K QPS, post which the same issue, the write bottleneck was seen, and the test eventually failed. Okay. So I'll touch upon all the performance bottlenecks which were faced during this issue. So this database system, that is MySQL database system, is a single master system. That means you can have n number of replicas, you will have a read scalability, but when it comes to the write scalability, it is a single master. The single master has to accept the write and send, or via bin logs, it is being traversed to the other available slaves. So therein we'll have the replication lag, and also there is a read after write consistency issue is also possible. And again is a commit latency, as it's a single writer master, right? When there's a flood of users logging in for OTP, asking for OTP, and the validation of OTP happens, there is a commit latency seen. All the queries started waiting on the commit in the process list. You can see that evidently. And this also become a bottleneck and increase latency and application failures were there. And third, the fourth important thing is non-instant DDLs. So you might ask, like, DDLs are instant in MySQL. Yes, there are certain DDLs that are instant, like column addition is instant. But the non-instant DDLs, that is when you do an index or when you do an existing column, that's modification of existing column, that is not instant. That means it go for a copy algorithm. So this customer has a huge amount of data. When they have to add a column, or sorry, modify a column or add an index, it takes a lot of planning and downtime, and multiple teams are involved. So it's operational issues that they have faced. This is not related to scaling, but operational issue. And the main important thing is when there is a huge number of writes or the waits happening in TB, the master tends to fail over. Okay, as there were a lot of writes in waiting state, the recovery of the system, that is the failover and the recovery, took a longer time and leading to a bad user experience. Okay, these are the database performance bottlenecks that were faced with respect to the current MySQL system. Okay, now we'll move to the next solution. So the customer came to us with this problem statement. So we wanted to address this write scalability issue, majorly the write scalability issues, and also this failover HA replication lag. So then we had a series of discussion, multiple series of discussion with the customer, and then we carefully thought. And also one of the important requirement was customer need to have a minimal code change at the application side, so that the time was very low, because the event was scheduled in next two months. So they wanted to have very minimal to zero code changes to proceed. Okay, so that is when we introduced TiDB. So for all of you, so TiDB is an distributed SQL which is completely open source. The main reason for evaluating TiDB is this TiDB is MySQL compatible. That means when your application runs, whatever the application which runs on MySQL can directly talk with the TiDB with the same protocol, no change in driver, the connectors, everything remains the same with minimal code changes. I'll say minimal code changes because certain things are not supported in TiDB, that is stored procedures, triggers, and certain other things as a normal distributed SQL it does not support. TiDB comes with both vertical and horizontal scaling. That means you can upscale the instance, that means change the instance type and move to a higher instance, or you can horizontally scale by just adding a node. That means your data will get automatically sharded. So this sharding is transparent. That means there is no change at the application. Your application will not even know that your underlying data is sharded. So, and also the data is automatically sharded. That means when you put a data into TiDB, it's automatically sharded and distributed. Okay, TiDB also has a multi-master distributed architecture. So I'll not go much deeper into the architecture. I'll just touch upon the architecture. TiDB is also an HTAP database. HTAP is hybrid transactional and analytical processing system. That means TiDB has a capability to handle both OLTP and the OLAP workload. Since it has two engines, we'll discuss in the next slide. And as we said, right, client wants to have a zero code changes at their end. So that is also one of the important reasons for choosing TiDB. And again, obviously, TiDB is completely open source. Okay. In the next slide, we'll discuss about the TiDB basic architecture. So TiDB has three components, that is PD, which also runs in a cluster. So everything is a cluster and comes with a decoupled architecture. That means each runs on a different individual nodes, okay, individual nodes or maybe pods. So PD is a placement driver, which is the brain of the cluster. It handles the metadata and the TSO. The TSO is basically for the distribution, and the distributed transaction comes into the picture. And more than that, PD also monitors the cluster scheduling, and major maintenance activities with respect to the cluster is done by the PD. And TiDB is your SQL front-end layer. That means it is the layer that talks the MySQL protocol. Your application can connect to TiDB. This TiDB layer is stateless. That means it doesn't store any data. So this TiDB layer is responsible for handling your connections and getting you the result sets, and also it connects with the TiKV layer to get the data. Okay, so this is, as it is stateless, you can add n number of nodes as to your application scalability on the connections and authentications. So next is a TiKV. So this is stateful, and this is where your actual data resides in the cluster. So TiKV is a key value storage, which is built on top of RogDB. And we have three boxes, right? It represents a node. We have minimum three because it runs in a HA configuration with a replication factor of 3. So, and this component, type flash, which is your analytical component, which is optional. Without type flash also, you can run your cluster. This type flash is built on top of open source ClickHouse. It is a columnar storage and which helps in the parsing of the analytics. Okay. So this is, so I hope you get a basic idea about the TiDB and its architecture. So now let's move on to the, back to the story, the migration journey. Okay. So migration. So when we discuss about the migration, the client was more skeptical on how we move the data. The data is very huge, and how we do that without with full consistency and zero downtime. So we adapted a zero downtime migration plan. This is a plan which we devised for zero downtime migration, wherein that is TiDB will act as a replica, that is similar to the other replicas, replica 1 and replica 2. TiDB will act as a replica for the current primary master. So how this is possible is TiDB provides a tool, which is also an open source tool, that is data migrator tool, which sits in between the TiDB and the primary MySQL, which helps in loading of the data. I'll explain how the migrator works in the next slide. Before that, so the migration was done in 2 steps. That is, first step, we took a structural backup from the MySQL, that is current MySQL, and we validated the schemas as per the compatibility of TiDB. That means in my TiDB, there are certain older character set, like example Latin Swedish one, which is not supported. We encoded them to the newer version, that is UTF-8 or whatever the client says, and then we loaded the schema onto the TiDB. And then we started the DM cluster. So the DM cluster pumps the initial load, and then it replicates with the bin log. Okay, so this is how the typical migration looks like. So as I said, right, DM. So the DM sits in between the source and the destination. Our source is MySQL and destination is TiDB. So migrator has 2 components. One is a dumper and a loader. This migrator is also built on top of MyDumper, which is a multi-threaded backup tool for MySQL. So the dumper dumps the data from the source as a SQL file, and loader loads into the TiDB, and it also note down the position, okay, of the bin log until what position the backup has been taken constant. Post which it starts a relay. That means like our normal asynchronous replication, it starts a relay from the bin log and syncs the incremental data. It's similar to that. It will also have a replication lag that can be monitored and things. So this is how the migration is done. Once the migration is done, okay, these are the migration highlights. So we had done the migration. It was 7 TB of data. So we were able to complete this 7 TB of migration within a span of 28 hours with full load plus the incremental sync via replication. Okay, with the help of DM we discussed right now. So DM has a mode that is physical data loading. What it does is the physical data loading converts the SQL file directly into a SST file, that is the TiKV storage file, and attach it directly to the storage layer. Thereby, it was the speed of restore was very much faster. And we were able to reduce the storage. That is, we had 7 terabytes in MySQL was translated back to 1.5 TB in TiDB, which is around 79% of storage saving on the TiDB side. And one important thing is this being a legacy application in the MySQL, so they had it was migrated initially from Oracle. So they had the primary key as decimals, okay, in certain cases, which is running as say. So the chief of the architects, like from the application team, product team, came to us stating that, so we want to make this change, that is the decimal primary key has to be changed as with a beginned primary key on the TiDB. So as I said, right, the structural changes, this was that structural change. We also, along with the incompatible changes, we also made a change to the primary key. That means whatever the decimal based ID primary key is there was changed to a begin based primary key, restored, and then we did the loading and it worked smoothly. Okay, so now the setup is all ready. So we have completed the setup, and the application team, they made an initial set of testing validation like count of star, is the data consistent, those things, and then they started doing the load test. So as similar to the existing environment, they started the series of load tests with respect to 10k TPS, 20k TPS, 30k. This is goes on. You can see from the bottom to the up. So this is the number of PD nodes, TiDB nodes, and TiKV nodes. As I said, it's a horizontally scalable with respect to the load increase and the latencies. To manage that accordingly, we started adding the loads. Okay, so if you can see in all the tests, that is 12k test, 15k, 18k, 20k, the PD remains the same. There is no change to the number of PD nodes. That TiDB and the TiKV will be the one which is changing accordingly. So initially it started with 15 TiKV nodes and 60 TiDB nodes. On all the way above, for to scale 3.26 million QPS, we use 56 TiKV nodes and 90 TiDB nodes. And with this, we were able to achieve the required QPS. That is, we exceeded the QPS. The expectation was to have 3 million, but we touched upon 3.26 million QPS with a P99 latency of 14 milliseconds. Okay. So it's all about the performance. Don't see about the cost here because it was about the performance. So this is a cluster size which we worked upon. So we had around 121 hosts deployed in this particular cluster, and this 35.6 you see is a memory. It's not a RAM, it's a memory, and this is a physical cores. So just I wanted to show you the size of the cluster. Okay, so to claim my points, right? So we had the load test. During the load test, these snapshots were captured. So this is the QPS graph which we had captured. It is like 3.26 million QPS, and you can see the duration as the same. And this is a split up of the QPS. So we had a commit, that means writes around 1.52 million, selects as equivalent as that, updates and inserts. Okay, so this is the overall QPS handled by this. And okay, so this is the overall QPS. Next, the client wanted to do a write scalability testing. That means when the huge of flood happens, that means the user logs in. So there will be OTP, I said, right? So that will be generated. So to simulate that use case, like they started hitting only with the write APIs to see what is the latency and also the throughput which is able to handle. So we were able to handle more than 300k writes. That means you can see the insert ratio as 282k, and along with some updates and with some selects as well. Okay, along with this 300k. Sorry, I'll take some water. We were able to provide a sustained write throughput during this testing. Thereby, we solved this write scalability issue. So this 300k is almost 2 to 3x of what Flipkart handles with respect to the big billion date scales. You can compare the scale. Okay, this is the happy path which we have discussed, and it was not achieved without any issues. So we had some issues, and we faced some issues, and we had also done some lot of workaround. Mostly, like 99% of the workaround was done on the database side. It's not on the application side. So the first issue is a floodgate issue. So first thing is, like we, as I discussed in the initial side, like for the second phase, when the team added Redis as a caching layer, there are certain points at high concurrency. Redis tends to fail. Okay, even though it is a managed service, it tends to fail. When this failure happens, the whole flood of connection that is comes to the database. Okay, and the database eventually chokes. Even when you have a huge number of systems, a sudden spike or a very short spike, that is a floodgate happens. It was not able to handle. So then we gone to the root of the issue, and we discussed with the application team what was the type of queries that is being handled at the Redis. So they said the Redis majorly handles the master tables. So the master table is nothing but a config based table. So those doesn't change much. Okay. So then we discussed upon, and there is a feature in TiDB. We started to put those table into caching. Okay. So there is a concept in TiDB that is called a cached table. So wherein when your table size is less than 64 MB in size and it is very less frequently updated, as in our use case, you can cache this table. That means like on the wire caching, you can cache this table in the TiDB layer, that is your SQL layer. So we added the caching for all these tables, that is master tables, 46 tables, and we started the load test, and it was very impressive that without Redis, right, it served the caching purpose, and by this we were able to remove the caching layer. That is, Redis was completely removed. Thereby, we were able to save some dollars for our customers. So this is one of the floodgate issue which we resolved with the caching table. And second is the hotspot issue, that is majorly write hotspot issue. This was seen in the load test environment. What is the write hotspot? See, for example, when you do a load test or an uneven calling of queries, the particular shard or the particular chunk of data will get highly utilized. This is a common problem with respect to the distributed SQL, that is distributed computing. So what happens is, when this particular shard get overused, that particular the data which resides in the particular TiKV or the particular type flash, which usage get high and other was not used. Okay, there is an uneven distribution of load because of this hotspot issue. So we identified a hotspot with respect to two of the major write tables. So we enabled a hash based partition, that is, the table was equally split and it was distributed. And you can ask, like, TiDB is already shared, why a hashed partition? So hashed partition, we tried to split the shards, that means split the regions and then scale it, but still, as it was using only two nodes, two of the TiKV or three of the TiKV nodes, it was not evenly distributed. So to evenly again distribute, we made a hash based partition to distribute it, so that the writes were equally transmitted. So with this change, with the hash based partition change, we were able to remove the key space. If you remember, we had two tables which were moved to the key space. So actually they were asynchronously syncing from here. So thereby we removed the key space use case as well, and that table was again brought back to TiDB itself after this feature. And third issue was connection imbalance. So as you might have seen in the load test, we had around 90 TiDB nodes. So we had all these 90 TiDB nodes under a NLB, that is a network load balancer, where the application connects to the NLB, and the NLB, based upon the things, it distributes the load to all the 90 TiDB nodes. That was the expectation. But with respect to the stickiness and skewness, like whenever the first node or the with respect to the ordering in the NLB, half of the nodes, or like 20 to 30% of the TiDBs, were highly utilized, and the remaining, that the nodes in the lower order or the farther was not utilized. The CPU was remained like 10%, 20%, and this caused an uneven connection distribution and also load distribution in the database. To solve this, we use type proxy. Okay, so type proxy is a balancer from the TiDB itself, so that it sits in between your application and the TiDB layer, handling the connection balancing as well as connection failover. I'm saying connection failover, but even like when a TiDB node goes down, let's say that particular TiDB node is handling 10 to 15 active connection, those connections are safely migrated to the next available TiDB node, and thereby your connection failure happens. So this is a main functionality of this type proxy. With type proxy, we are able to achieve equally distributed load of connection, and with that we were able to handle 60K connection, that is 60 connections per second was handled. And even with the highest instance type, right, so we had only a limit of 16K. So this was a greater win what we had with the type proxy. Okay, so the final thing, this is the most important thing. As we said, the client wants to go with a zero change pattern, right? So actually their application is bound to an framework. Okay, so there is a minimal change, or the minimal visibility of change that is to be done in the framework. So they want all the changes to be incorporated into the database layer. So we used SQL binding. So in certain scenarios, as the table had multiple indexes due to a wrong statistics or a wrong statistics collection from the optimizer, the TiDB was choosing a wrong query plan, even though it had an index. So this is quite common in the optimizer. Even in MySQL, you might give the hints, right? Use this index. So that is actually a code change. You rewrite the query to use this index, and this particular change will be done at the application code for the particular query. But here it is not the case. Here you say that For this particular query, you use this plan. The SQL is like binding that query with the query hash as well as the digest hash. It will be on the database layer. The whatever you say, like we create a global binding, use this index. This is at the database layer, so it has a inside a SQL binding table. This rule is saved, and from the application side, it will be a normal query which is being fired. When this particular query comes in, it matches a pattern. Always this this query plan is being stick to it, and it will be used irrespective of the values. Let's say if A and B changes, right? Even in that case, it is a digest value. It is matched and it works perfectly. So we had created multiple SQL bindings to make really a zero application change at the application layer. So we are able to achieve with zero code changes. This migration was done with zero code changes. Okay, and this is the final thing. So this was a bonus. This was not even in the picture, but we asked to explore. We did that. So real-time analytics, like with the type flash. So they were using, this client was using BigQuery for the analytics. Therein they use the bin logs. Bin logs will transfer to some other service, and from the bin logs they write to the BigQuery, and they get the reports. So then we evaluated type flash. We added type flash. So the beauty of type flash is, like, it is not necessarily that all the table needs to reside in the type flash. You can control the level of replication to type flash at a table level. Let's say for the analytical purpose, they had only 20 tables like transactions. So how many users are logging. So those information were present in particular tables. Those tables were alone moved to the type flash, uh, which removed the dependency of external bin logs and those things. And the reporting time was reduced from 1 hour to 7 minutes. Okay. And as there was no replication lag, since type flash syncs from the same wrap group lag, there is no replication lag between the type flash and the type KB. Okay. Here are the outcomes. I'll discuss briefly on the outcomes. So we had a query improvement, like 4x of query improvement with high, at high concurrency. Are able to handle with 14 millisecond. Zero downtime cutover during the migration, yes, which we discussed. There was zero downtime as well as zero code change migration, which we done. And with the unified architecture, that means the external dependency of Redis, key spaces, and other components like NLB were completely removed. Is a complete unified architecture which satisfies their application use case. And scale without re-architecting, yes, without zero downtime change, they were able to scale and re-architect this application. And real-time analytics with the type flash, they are able to reduce the analytical, that is real-time analytical window from 1 hour to 7 minutes, which is a greater win. And storage reduction, yes, we reduced the storage from, say, with a storage saving of 79%, and no replication lag as it's a multi-master and the raft-based replication happens. There is no replication lag in the system. And a simplified scaling. Yes, you can add the nodes when the cluster is online, and also you can remove the node when the cluster is online. So there is scale in and scale out operation is completely online. It's automated scaling. And remove the failure points. So as I said, the replication factor is 3. The point of failures and the failover, those pain is completely removed, is a raft-based failover, which is okay. And having, after all this said, also they wanted to have a rollback as a safe point. So we decided to build a rollback system. So here the rollback system looks like. So as we said, the DM will be replicating from primary, that is primary MySQL to TiDB. From the TiDB, we built a TiCDC. This is also in open source. So from TiCDC, it replicates back to the MySQL system. Okay. Thereby, even if the while during the cutover, when there's an unknown issue or an unknown failovers, they want to roll it back, they can roll it back. So TiCDC also speaks multiple protocols. They can write directly to a S3 storage and other things as well. Okay. So there ends my talk. You can shoot out your questions. Thank you.
Yes, we shall move on to the Q&A. But before that, I would like to thank you, Kabilesh, for walking us through the migration story. Moving a live SaaS platform with huge users from MySQL to TiDB, keeping it running and still improving performance is not a small thing. We not only saw the real numbers, we saw the real steps, real problems, and although also the trade-offs, I would say. So we have heard a complete story behind the migration. So now we will move on to the Q&A. So attendees, please post your questions in the Q&A or chat, and I'll read them out for Kabilesh.
Hello. Hi, Kabilesh. It's Nagarajan.
Yeah, hi Nagarajan.
Yeah. So two things I just want small clarification. One thing is the first one, the storage when you migrated. So from 7 TB to it was reduced to 1.5 TB. So how it was happened, like that was my one of the questions. And the second one is, and when you mentioned that when you this nodes, the counting of nodes, there when you achieve the final output, there were some 3, 90, and 58, right? So how it was actually calculated or how it is managed? I didn't understand that particular part actually. So these
Okay.
are the questions. Yeah.
Okay, so I'll answer the first question. So how the 7 TB was translated to 1.5 TB in, the thing is like TiDB comes with a RocksDB storage. That is, it is by default, it provides a compression. That means the data which is present in MySQL, so MySQL uses a B tree, it uses an LSM tree. Okay, so it is a level based compression. So we did not enable any special compression mechanisms at the TiDB level. So when you put the data, directly move the data from MySQL to TiDB with the default TiDB compression, it comes to the 1.5 TB. Okay, so there is no extra magic or nothing done on that part. And coming to the second question on the scaling part, so TiDB is built with a horizontal scalability. Okay, so that is where the other traditional databases like RDBMS fails. So that was the main reason for the MySQL not scaling, and also it comes with a shared nothing architecture. Here, TiDB comes with a sharded architecture. When you add a node, let's say the TiKV node is added, the scale improves exponentially, horizontally. That means when you add a node, the particular set of data shard rebalances, and it moves the chunk of data to the TiKV nodes. Thereby, it can start accepting the more load or the more concurrency as per the requirement of the application. So based on the application TPS, let's say we were discussing, right, 10K, 12K, 15K. Based on that, when we hit a bottleneck with respect to the database layer, let's say at 25K TPS, we had let's say 40 nodes, but the final was 56. When we saw a latency at the DB layer, when the DB latency increases, we just add a node to compensate the concurrency. So this is how we did.
So that means why there is a difference of that 90 and 90 TiDB nodes and why there is a 5830K nodes? That what's the difference?
See, there is, as I said, TiDB is a serverless component. Okay, there is no intervention of TiDB because it does not store any data. It is only for the connection and the authorization. So to reduce the latency at the application layer, we were keeping the TiDBs in the same zone as MySQL. So that is why we had a 90 TiDB nodes, and also to handle more incoming connections. TiKV has no relationship with that.
Okay, thank you.
So basically, TiDB is for the query engine and TiKV is for the storage.
Storage engine, yes, exactly.
So I have one question. See, basically, this TiDB is a distributed database inside, right? So when we have a joins, complex joins, so then the query, my join query is going to be executed on multiple sharded nodes, right?
Yes.
So the query response, whatever you are showing, that totally depends on the type of queries that application is using, right? So let's say if it is using complex joins, then the latency will be more than RDBMS latency, right? That there is a possibility, correct?
No. I'll explain this. So this is a very good question. So when you have the multiple joins, so based upon the data distribution, let's say when you are talking to MySQL, when you join, the table will be present in a single node. A single node, it joins immediately and tries to get back to you. But when you comes for a distributed architecture, the table data will be present across all the nodes or maybe some nodes, let's say, okay,
Correct.
based
Correct.
upon the database. TiDB has a first the query goes to the PD and it provides an optimized plan. Okay, so this is a
Correct.
I'll touch upon the optimizer as well. So each TiKV, let's say TiKV1 is responsible for, let's say, data from A to C. Okay, other is so when you join, in case of a full table join, okay, it is not recommended even in the RDMA system. When there is a full table scan happens, each TiKV will do the computation. Let's say based upon the query plan, there will be multiple parallel processing happening. Okay, parallel processing happening. So the each parallel process will fetch the data from the each TiKV nodes. Also, each TiKV has a co-processor. There's a processing component in the storage layer. Let's say you make a count. Let's say you run a count of star. So let's say A and B has to be added, like whatever the shard which is there, right? Let's say shard 1, that is TiKV is responsible for 1 to 10. It will compute the addition of 1 to 10 and send it as a result. It will not send it as a data. Okay. And the TiDB will combine them as per the result and send you back. So that is how.
So basically, that shuffling will not happen. So
shuffling will not happen. It's not
the aggregated data will go
aggregated. It's not that all the data will be pushed to the TiDB. So some computation happens at the TiKV layer as well. Did I answer?
So another question. Yes, yes. So another question is basically by migrating to TiDB, we achieved more number of queries as well as more storage overall. That is the goal. What is the goal for the this migration for OTT company?
Okay, the goal for this company is not about not about the okay storage or cost saving or nothing like that. So they wanted to scale for 3 million QPS, that is 3 million concurrency within a latency of P99 latency of 14 milliseconds. So this was the goal.
So that was not possible in the relational database RDBMS. Possible. So basically, they are trying to improve their metrics.
Metrics, yes.
This.
You know this OTT scale, right? So what happens when Kohli was means batting at 99? Suddenly the spike will happen. So this cannot be handled in the RDBMS system. So that is what they are trying to address with this architecture.
So one question actually, since I come from a multimedia background, so the number of users are increased suddenly. So that the data comes from the CDN, right? So why there is a lot of write QPS on the database?
So the CDN just means CDN is a central
media
caching
content.
area content.
For the media content, it will come from the CDN. But on the database, why that load comes? What is that they will write? Is it like the position of the playback that they will?
It's not the playback. So it's like let's take an example, like the streaming is ongoing. So CDN is for the content. It's not
media
for
content.
the media content. It's not for the subscription.
Correct. Subscription suddenly will it increase?
No, not it will not increase. Subscriptions are not suddenly will not increase. But let's say I'll just take the same example. Kohli is batting on 95. So you are watching it and you will say to a friend he is on 95. This message spreads in WhatsApp or somewhere. So everybody will try to log in. Am I right?
Okay.
Content you can get from the CDN, but the authentication, like you'll be using mobile, right? Let's say you are not logged into that OTT platform for a longer time. Let's say it auto logs up, right? Then it has to when you log in, you have to check your premium. So your content is you have a active subscription or not. First thing. Then if your OTP is like you are logged out, you have to send a OTP. So these are the things that will come here. It's not about the CDN.
Okay, so OTP is one, right? But the subscription details reading, that will be read QPS.
Yes.
So
write QPS will also happen. It's not about only read QPS. They control all the data, right? At what time you log in, what are the contents you are watching, how many times you have served. So every data is collected. So it's all writes.
Okay. So another question is the TiDB that you migrated. So TiDB also has a service, right? Managed service. So this is from the open source you set up and then
Yes.
migrated?
It is on the open source, yes. We set up it on a VM.
like some sort of Kubernetes or something.
Not easy to initiate.
Easy to initiate. Okay.
Hi,
Okay, thank you.
Ranganath. Thank you, Ranganath and Natharajan, for those wonderful questions. We have time restrictions, so we have to quit it or to stay on time. And if you have any other questions that are not registered here, please reply to the follow-up email or reach out to us on LinkedIn, and we will be happy to respond. Thanks again, everyone, for joining and staying till the end. Big thanks to you, Kabilesh, for sharing so many details from a real project. And final quick reminders before we close. You will receive the recording and slides on the email you used to register. And if you want to discuss your own database setup or a possible migration for you, you can reach out to us through the Mydbops website on LinkedIn or by email at info@mydbops.com. And have a great weekend and wish you all a very happy new year in advance. Hope to see you in the next webinar. Thanks, everyone. We are closing the
Thank
session.
you. Thanks, guys. Thanks for the support.
Thank you. Thank you.